Hi there. So this is a lesson that is part of one of the courses that we do called Introduction to Algebraic Thinking, where we take students through the why of algebra and the how of algebra so that we can give them a very great foundation that powers them through middle school and high school. So in this particular lesson, we're going through a pool border problem. In this problem, students take on the role of the constructor of a pool, and essentially what they're meant to do is to find the number of tiles that should be bought so that they are able to create the border of a pool. And the pool is construed as a square matrix. And so the students are now meant to find out in what way they can calculate how many tiles are going to be purchased, okay, for the border of the pool without counting it. But before now, they have gone through what it takes or what it means to create or derive the rules for finding out, something, a pattern. So they are meant to now extend that here and say, okay, how do we find out how many tiles surround this pool without counting it? And so after a little bit of deliberation, they discover that they can do the length of the pool, which is in this case 3, okay, times the 4 sides, and then plus the 4 corners. In other words, the length of the pool, all right, which is in this case 3, times the 4 sides, 1, 2, 3, and 4, and then add the 4 corners, because everyone is going to have 4 corners. Everyone is going to have 4 corners. And this gives us 16. All right, so they share with the class, and then they are given another problem. Now this is a pattern, and it is growing. So the first was a 3 by 3 matrix, and the second one is 5 by 5. And they figure out that the same rule can apply here, where they have a pool with length of 5 times 4 corners, or rather times 4 sides, and then plus 4 corners. And that gives them 24. So 24 tiles are going to be purchased that can be the borders to the pool. Now what they've done is to understand a little bit of what we call iterative rules, which is when you see the occurrence of a problem, can you create a rule to solve that problem? And when that occurrence grows, or when that pattern grows, can you create a rule to solve that same pattern? Here, we're now given a pool that is of side length 10, and we would see that it generally goes through the same solution, but in this case, we have a small animation to show if they are right or wrong. If, for instance, we missed it by saying, say, 12, then we will see that the solution shows that they are wrong because it adds in a number of tiles that are not meant to be there. So I, as the person who is buying tiles for this pool, can already quickly see that, hey, I've bought too many tiles. Okay, so we can check it again and say, okay, 13 times 4 plus 4, and then this just helps us to know if our iterative rule is correct. Next, the students will try it again. However, we now give them an occurrence of this problem where where one side is unknown. And so after a little bit of deliberation, they realize that, oh, since they have given us that the length of the pool is n, therefore we can say n times 4 plus 4. This, from here, students begin to understand what we refer to as a general rule or an explicit rule, which is essentially a rule that occurs for any occurrence of the problem, whether it's the first stage or the second stage or the nth stage. So this rule should be able to work for as many occurrences of this problem as possible. So let's see if we can buy some tiles with our rule. All right. The first problem says you have you have to buy tiles for 10 pools for 10 different families, and that the first is a 12 by 12 pool. As you can see, the rule uses the 12 by 12. The rule takes the 12 by 12 pool and buys 52 tiles for it, which is correct. And the second takes an 18 by 18 pool and buys 76 tiles for it, which is correct. So essentially, the students have now been able to derive an algebraic expression using algebraic notations that can be used to solve a problem regardless of the occurrence. And this is how we begin to introduce algebraic thinking to them. In this particular slide, we find that the students are now giving another kind of problem where a mistake has been made and they want to figure out where the mistake has been made. The mistake says that having bought tiles for 5 families, one of them is wrong. And so with a little bit of mathematics, they can figure out easily that Cruz is that the first person Cruz is the person who the tiles were wrong. And the reason is because n times n plus 4 should give 226. So therefore, if you remove 4 from 226 and you divide it by 4, it should give you an integer. But in this case, it gives you a fraction, meaning there was a problem. But it gives an integer for every one of them. And there you have it. This is how we introduce students to algebraic thinking. And we go on to slightly harder rule-making lessons, but then it helps them to understand the foundations of algebraic thought, why we do algebra, and then go on to now know how to do algebra all the way to calculus.